and the beta kind of lactones. Right, nomenclature of amides. Biggest thing here is very similar to the esters, where we have a thing off of, right? This is our amide portion. We have something off the nitrogen, right? We have this parent chain piece. So in this case, we say an N to indicate it's off the nitrogen, N-cyclohexyl, right? That's this piece. Or if we label this A, that's this portion, N-cyclohexyl. Propane, 1, 2, 3, propane. So that makes sense. Propane. Amide, right? So amide is the suffix here in this case. So now if we put more things on, so let's circle the amide part, right? So amide. What's off the nitrogen? Well, there's a methyl and an ethyl, so we say N-ethyl, E before M, N-methyl, pentane, because there's, again, 1, 2, 3, 4, 5, so pentane, 5, amide, N-methyl, N-ethyl. Here, again, if you have, now you have 2 ethyls off of the parent, which is an amide, so you say NN diethyl butanamide, because 1, 2, 3, 4. Nomenclature of lactams. So the cousin of a lactone is a cyclic ester. A lactam then is a cyclic amide. Again, I'm not going to ask you to know much more than can you identify something as a delta lactam because it's alpha, beta, gamma, delta. Again, this is the amide portion. The nitrogen is attached to the delta carbon, so it's a delta lactam versus a gamma lactam, which is alpha, beta, and then a little gamma there, versus a beta lactam, which is alpha, beta, right? Beta referring to where the nitrogen is connected to which carbon is the beta carbon. So I want you to make sure you know delta, gamma, and beta lactams. Just know how to identify what they are. Not necessarily name the whole thing. Just know this bottom portion. Here are just some examples. I'm not going to really harp too much on knowing all of these. Phosgene is a diacid chloride, carbonic acid, right? It's with 2 OHs. A carbonate is 2 esters. A urea is 2 amides. A carbamic acid is an NH2 and an OH. And a carbamate is an H2OCH3. All right. So you should know what a urea is and a carbamate. Carbonate is a urea, and a carbamate. So I would say these are the 3 I want to make sure you know. A carbamate, amide and an ester, urea, diamide, carbonate, diester. All right, so done nomenclature. Let's start talking about some of the actual reactivity about some of these carbonyl compounds, right? The C double bond O, right? The generic C double bond O. This is what do we know? Some things we know. We know that this carbon is sp2 hybridized, right? We know the bond angles are 120, right? That's shown here. If we look at a molecular orbital picture, we can see a little bit more. We can see the bond angles that were between here to here is actually a 90-degree bond angle between the pi bond and these sp2 hybridized carbons, or sp2 hybridized orbitals. So if there are H's here, or actually doesn't really matter what's there. The biggest thing to remember is if you have a p orbital, you have an sp2, an sp2, an sp2. So an sp2 hybridized atom has a p and 3 sp2s. And the p orbital, of course, makes pi bonds, right? As shown here, these 2 pi, this is a 1 pi bond and a sigma bond between them. All right, so remembering sp2 hybridized, 1 pi bond, sp2 orbital, sp2 orbital, sp2 orbital, p orbital. If you go back one slide, you can remember, look, there's a negative charge, the plus charge, a negative and plus in this resonance form. What we were calling the non-carboxylic acid derivatives. So I'm just going to draw a ketone and I'm going to draw an aldehyde. And the difference here is something like an ester, right? An ester or a carboxylic acid or an amide, right, the group off of there, right, these groups, right, whether or not they're good leaving groups has to do with whether, a lot of it has to do with whether or not they can do these resonance structures as well, right? Ketone and aldehydes cannot do resonance structures. That's another big difference between these acid derivatives and the ketone and aldehyde. Now, what does this resonance do if we're going to highlight the carbon of the carbonyl group? Right? That's the electrophilic site. So the more resonance you do, actually, makes it less reactive, right? It makes these carbonyls, the less reactive carbon of the carbonyl. Right? More resonance will actually make this less reactive. Right? So actually aldehydes and ketones are more reactive than esters, acids, and amides. Right? At least at this carbon, right? If we're circling that carbon there. So resonance actually makes this less reactive at these carbons, right? Because of this resonance structure. So because of that, there's more of a it's a polar bond, right? So if you look here in alcohol, of course, it's really high boiling because of H bonding, right, with itself, hydrogen bonding, that OH. But now if you look at esters, these other ones, there's some interesting things going on here too. So I would highlight anything that can do hydrogen bonding, right? Carboxylic acid and its amide with NHs, super high boiling point, right? Nitrile appears to have a really high boiling point too. There must be some sort of, right, intermolecular force going on here. Obviously it's not hydrogen bonding in the nitrile's case, but still must be pretty strong. Then if you look at ketones and aldehydes, and ethers are real low, right? So they must have very low intermolecular forces, very weak ones. Alcohols are high because of H bonding. And then esters, acid chlorides, and aldehydes are all, these guys are kind of all in the same boat. They're polar, but they're not super polar. And boiling points around there. But you can think about resonance structures making them more, right? So the biggest thing is thinking about here is hydrogen bonding, right? If you can do hydrogen bonding, it increases your boiling point. You have stronger intermolecular forces. If you can do resonance, usually that increases your boiling point. Nitrile must have strong intermolecular forces because it has such a high boiling point as well. All right, so here's just showing a picture of that. So you can see the strong dipole interactions here. And here you see the nice hydrogen bonding dipole interactions also with an amide, right? So amides have really strong interactions, right? Because the nitrogen can donate electron density so well. So that resonance structure for an amide is much higher than it is for carboxylic acid or an ester because the nitrogen, less electronegative, right? A nitrogen is less electronegative, so it's more likely to do this resonance form because the nitrogen is more likely to donate its lone pairs in resonance, right? So you're going to see a lot more of that going on. So amides particularly have really high boiling points, and we're made up of amides, so that makes sense. We don't boil very easy, right? We have strong intermolecular interactions, so that's a good thing. Kind of a fun side note, you can see as you add carbons, right? Think about it, as you add carbons here in these fatty acids, more and more carbons, the boiling point, melting point goes up because you get more and more greasy. Kind of like thinking about us. You can think about unsaturated ones. So if you start putting alkenes or double bonds in there, you probably know cis fats are better for you, right? Because it's a cis alkene. It's going to be harder for these things to stack up, right? So saturated fats, you know, are bad, right? You can think about these all lining up on top of each other and clogging up your arteries. Unsaturated fats, the cis ones are better than the trans ones because the cis ones form like kinks, whereas the trans ones, you can see I'll put a double bond right there, you could stack those up again. So trans unsaturated fats are bad for you again because literally the molecules stack up and clog your arteries. So there's a bunch of other fancy ones here. Here's a nice picture. No double bonds, but you can think about how well these things could stack up, right? Versus this one has a little kink in it, has an alkene that's a cis alkene. These are going to be harder to form, to basically clog up your arteries. All right, excellent. So now we're on to really hitting the point about the reactivity. So we talked about nomenclature, we've talked about bond angles, being sp2 hybridized. Now, how does this actually work? So this is an sp2 hybridized carbon. We talked about doing substitutions of whatever Y is here, right? But we know we cannot do no SN2 reactions on sp2 carbons, right? None. So we're going to do a substitution. We're going to lose this. This is going to be substituted. But we're not going to do an SN2. We're going to do a different mechanism. So we know that this carbon of the carbonyl is delta plus, right? It's attached to the double bond oxygen, so that's a delta plus. So this is a good electrophile. That carbon's a good electrophile. So nucleophiles are going to attack there. But they can't attack and straight kick away the Y minus because the bond angles don't work. So we have to do a different mechanism here. What that mechanism is called is a addition elimination. So you first do an addition, right? We first add in, right? Have a nucleophile attack the sp2 hybridized carbon, kick up the pi electrons. We form something called a tetrahedral intermediate. Notice the carbon here was sp2, and then it became sp3, so it's the addition. In this tetrahedral intermediate, now we have a choice. We have two things on there. Right? We can either get rid of Y or Z, or we can get rid of Y. And whichever one's a better leaving group is the one we're going to kick out. Right? So Y, in this case, is a better leaving group. So we added in, we went from sp2 to sp3, tetrahedral intermediate. The electrons in the oxygen, which they just got, came back down, kicked out the better leaving group, which was Y, and reformed the pi bond, hence the elimination part. Right? So this is the addition. Here's the elimination. Reform the pi bond, as those eliminations are. Right? Kick out the Y, and the better leaving group is gone. So again, they like to use the terms base, then reactant. Basically, don't stop and think about what this is an equilibrium process. So let's just circle Z minus and Y minus. Really depends on which one's more reactive. If Z minus is more reactive, right, it's going to want to react. So the reaction is going to go that way, right? Z minus is going to attack, do the addition, form the going from sp2 to sp3 carbon, tetrahedral intermediate, kick out the better leaving group because Y is, in this case, less reactive. So it's more likely to sit there and be stable. And then we get the elimination. They use the term weak base. I just think you stop and think about what's more stable, right? What's a better leaving group? Is there resonance? Is one larger than the other? Which one can spread the charge better? Which one's more happy with the negative charge? Right? And I'll show a specific example in a second. So what can sometimes happen, right? Remember, these are equilibrium processes, so we can shift equilibrium. But if Z minus is essentially less reactive than Y minus, right? This reaction's not going to go very much, right? It's going to be, right? It's just going to kick back out. The Z minus will add in. We'll do the addition. We'll do the elimination, but we'll get back to the same thing we started with because Z minus is the better leaving group. If the two groups are similar, so let's say one's Cl minus and one's Br minus, right? Pretty similar. Br minus is probably a better leaving group. It's a little bigger, but we're not going to make a ton, right? If let's say Z minus is chlorine and Y is bromine, right? Bromine, well, maybe we'll get 70% of this, but we're gonna always end up with still with 30% of this, right? Just because the difference in reactivity between chlorine and bromine isn't that great, that sometimes we will kick out Z minus again and go back this way, right? So we'll get a mixture of reactants and products, right? So we really want to see the difference, right? Essentially in that leaving group, right? How can we shift equilibrium? Again, I just think of it as leaving groups. Don't worry about the basicity part, right? Which one's more stable, right? If this was this was Cl minus and this was Br minus, right? Maybe a 70-30 ratio would be about right for them sitting there in the actual reaction mixture. So let me show you an actual problem here.